Wait, can I? All right, so first, we're gonna do 2 days of transforming. You guys should know from your extensive integrated math career that transforming means shift up, shift down, shift right, shift left, steeper, wider, or flipped. Those are your different transformations. And we're not going to do any of that in scatterplots. Okay, however, sometimes someone does a study and their data does not come out aligned. So we talked about this, right? Didn't I tell you guys to be careful when you just have like summary statistics and you didn't get to look at a picture? Okay, so let's take a look at this page in your packet. By the way, whoever made our textbook made these beautiful graphs and summary statistics for us. Yeah, so we don't have to do all of this ourselves. Okay, so imagine that you're doing a study. This particular study is about the length of a rockfish and its weight. So these coordinate points are all different rockfish, and they're saying the longer the rockfish, the more it weighs. That makes sense, right? The longer a fish, the more it weighs typically. Okay, but these four chaps who did this study, I'm picturing them out there like in their waders, grabbing fish, measuring them, weighing them. Unfortunately, they come back to the lab, they enter all these coordinates into the computer, and they're like, oh crap, it's a curve. Okay, they will not be stopped. What they do is they take software. So I don't want to scare you. I don't want you to think that we're going to be like trying to figure out how to make this align. There are just different settings in this software that you can try different stuff. And what they did was they cubed, so scrolling down, they cubed all of the x's and it came out to a line. Okay, let me say this again. Their original data was a curve. They were not happy with this because they want to use linear regression, but it's not a line. So they messed around, basically guess and check. They cubed all of the x's and it came out to be a line. Okay, are you with me so far? Okay, now because I'm a giant nerd, this is the little bit of theory I was going to talk about. I messed around in my calculator and I was like, okay, this is a cube root graph. So this could be this little bit of a cube root graph like this. Do you see it? Okay, and how do you undo a cube root? Cube it. Right. Okay, so this is what I'm thinking. I think that the original graph was some transformation of the cube root of x. And so what they did was they cubed it to make it into a line. Okay, you do not need to do this. You don't need to figure this out. That's not a thing for you to do. I'm just letting you know this is probably what happens in research. Okay, now what we need to do is figure out, so first let's answer this question. What is transforming data and why do we need it? Transforming data uses inverse operations. So basically undoing things. Typically powers, roots, please listen, and logarithms. Today we're going to work with the powers and roots, and Monday's going to be logarithms, just so you know. On the x and or y values. So they might do stuff to the x and the y, and the one we looked at, they just cubed the x to force the data to be linear. Transforming data uses inverse operations, typically powers, roots, and logarithms on the x and or y values to force the data to be linear so that they can run the linear regression software without having the form be curved. Okay. Now, we are going to state the equation of the regression line. So come over here. And we're going to label a couple of things, and I'm going to highlight a couple of things. So if you have a highlighter, go ahead and grab it. And what I'm trying to do here is I'm trying to teach you to be detailed in analyzing what's happening in the graph. So here I want you to notice, oh, y is its usual self, it's just weight, but the x is cubed. So what I'm trying to get you to see from this graph is that y is its usual self, just plain weight, but the x is cubed. If you have this instead of the graph, you can tell that this is just regular y because it comes first. Do you guys remember yesterday we said the response variable usually comes first in the regression output, and then x cubed. Do you guys, by the way, all know that this little up caret means cube, just like you type it in the calculator? Okay. All right. You can also tell here that you have x cubed. Okay. So your question is, what does that mean for the equation? So we're going to go take this and go back here, and it says state the equation of the least squares regression line. Y hat is going to be its usual self because y was its usual self. And then we're just going to say equals. A is the constant. B is the slope. I'm just going to round it to 0.0147. But x is cubed. Let me put these two things right next to each other. So y is regular. Are you guys with me? Okay. The constant is 4.066. The slope is 0.0147. And then instead of just x, it's x cubed. Okay, now it says define any variables you use. So x equals length in centimeters, and y hat equals predicted weight in something. Grams? Okay, any questions about how I got this? Okay, can you guys take a minute to write this next step, please? Yeah. Would you believe me if I told you this was the end of the notes?
I would not believe that.
It's true. I wouldn't joke about such a thing. No.
Or we could just do, what are we doing on Tuesday? No, what is it though? Okay, but what actually is it? Oh, it's whiteboard FRQ day. Like I give you the College Board FRQs and you guys do them in the groups. Ah, it's fun, I think. Better than sitting here listening to me. Do you guys have it? Does anybody need a minute? Josh needs a minute? Okay, guys. Okay, use the model from part A to predict the weight of a rockfish that's 36 centimeters long. Easy. Y hat equals 4.066 plus 0.0147 times 36 cubed. You just have to actually make sure to type that in the calculator instead of just 36. Now it's 36 cubed. $689.909 grams. Any questions about how to do that? So you put the equation, just make sure to put the transformation in properly, and then just apply the proper math to it. It's not a big deal. Like I said, it's not the hardest day of stats here today. It looks like it though, it looks fancy, but then you get into it, you're like, no. Okay, now flip the packet over so you're looking at this side. Okay, and this time the length is the usual, and the y is cube rooted. The length is usual, and the y is cube rooted. So I have the cube root of y and plane x. Okay, so I'm going to attempt to show all of this at once. What I'm going to do is I'm going to put y hat, and then I'm going to cube root over top of it. So put y hat and then cube root over top of it equals a is negative 0.0220 plus 0.2467 and then plane x this time. So cube root of y plane x Variables are defined the same as the original and the same as the other one. We have to do our math a little bit differently. No, let's just listen. Okay, so I've got it all written in. And then I'm going to do negative 0.022 plus 0.2467 times plane 36, which is 8.8592. You're welcome. Okay. Now, how do I undo a cube root? Cube both sides. Did you see the difference between transforming with roots and transforming with powers? So the moral of the story in this problem is these two problems are just be super careful with what's on the axes. I would write it, on there. So just be careful with what's on the axes when you translate to your equation. Plug in as usual, but then just undo till you solve. These are not hard. And I'm done actually. Oh, I'm not. There's a joke. Oh, I actually really like this joke. Super excited about it. I've been thinking about it all day. It's one of my favorite jokes. It's pretty good. Okay. Did we figure out why transforming is necessary? Did we transform linear equations through powers and roots? Do we make predictions? Yes. Okay. Oh, you can't see this. Hold on, let me move the thing. Okay, it says, if she loves you more and more each day, then by linear regression, she hated you before you met. Like, loves you more and more each day, then before you met, she hated you more and more. Like, think of the line. Backwards. It's good.
I'm in on the joke.
It's a little cerebral, I understand, but it's very funny if you think about it. See, those two are gonna be married happy someday. By linear regression. Oh, he does look like 30. I wonder if he's wearing bell bottoms under there. Yes, yes. Only if you like my linear regression joke. Do you guys know how hard it is to find a linear regression joke?